February 16, 1949. Chalgrove Aerodrome, Oxfordshire. The morning is gray and overcast, the sort of English winter day where the clouds seem to press down on the earth itself. A modified Gloster Meteor fighter aircraft sits on the runway, its engines running, creating a low mechanical drone that vibrates through the cold air. In the cockpit sits Squadron Leader Terence Spencer, a veteran test pilot with nerves of steel and the kind of record that made other pilots simultaneously admire and pity him. He is about to do something that nobody in the world knows for certain can be done, whilst moving at nearly 400 miles per hour. He is about to eject from the fastest aircraft ever built. The hatch above him closes with a solid metallic thunk. Around him are sandbags positioned inside the fuselage, a desperate safeguard against the forces he is about to experience. Spencer runs through his mental checklist one final time. His hand hovers over a small lever. In a few moments, the entire trajectory of aviation safety will change forever. But first, he must survive what the engineers promised would not kill him. Most of them were not entirely certain it would not. This is the story of the ejection seat, and how British engineering innovation transformed aviation from a deadly gamble into a reasonably survivable profession. It is a story of obsession and sacrifice, of engineers who designed their way out of an impossible problem, whilst test pilots paid the ultimate price to prove the designs worked. More than that, it is a story that remained half-hidden for decades, obscured by secrecy, minimized by military bureaucracy, and deliberately forgotten by men who survived what should have killed them. The ejection seat saved thousands of lives across the globe, yet the full history of its development, and the men who died bringing it into existence, was never properly told. By 1943, the problem had become undeniable. Aircraft were faster, stronger, and more sophisticated than ever before. The Hawker Tempest could exceed 400 miles per hour. The de Havilland Mosquito combined speed with devastating firepower. Pilots who operated these machines were no longer simply flying. They were piloting weapons platforms capable of traveling at velocities that seemed to belong to the realm of science fiction rather than engineering reality. Yet in these magnificent machines, there remained one utterly primitive feature: the same basic cockpit exit system that pilots had used since the days of canvas and wire. When an aircraft was crippled or damaged, the standard procedure was simple and nearly always fatal. The pilot would attempt to turn the aircraft away from populated areas, reduce speed as much as possible, and then attempt to extract himself manually from the cockpit. He would either struggle out through the sliding canopy if he had time, or he would simply abandon the aircraft entirely, hoping that the slipstream would not pin him against the fuselage as he fell. Estimates suggest that somewhere between 70 and 80% of pilots forced to abandon fast military aircraft simply could not get out. They died in their cockpits, either from the G-forces that held them immobilized or from collision with the tail section of their own machine as they attempted to jump. These were not glorious deaths. They were mechanical failures, the predictable outcome of putting fragile human bodies into increasingly violent situations without the proper mechanical assistance. The Royal Air Force was losing pilots at an alarming rate, not to enemy fire, but to the simple physics of high-speed aviation. Fighter pilots, often the most skilled and most irreplaceable men in the entire force, were being murdered by their own aircraft's speed. The situation was intolerable, and yet the solutions seemed impossible. How do you eject a human being from a cockpit moving at 400 miles per hour without turning him into something unrecognizable? How do you accelerate a man from zero to whatever velocity is necessary to clear the tail of the aircraft in less than a second, without destroying his spine in the process? How do you ensure a parachute can actually deploy when the pilot is tumbling through air at velocities that tear the breath from his lungs? The problem seemed less like an engineering challenge and more like a riddle from classical mythology, the kind of impossible task set for heroes with the expectation that they would fail. Two brilliant engineers began wrestling with this problem in the mid-1940s. James Martin and Valentine Baker had founded Martin Baker Aircraft Equipment Limited in 1934, initially designing aircraft seats as a sideline to their main aircraft manufacturing business. By 1943, they had relocated to Denham, near Uxbridge in Middlesex, and had begun to focus almost exclusively on the problem of pilot escape. Martin was a man of fierce intellectual intensity, driven by a conviction that this problem could be solved through rigorous engineering and methodical testing. Baker was the methodologist, the one who insisted on safety margins and comprehensive analysis. Together, they embarked on a project that would consume the next several years of their lives. Their fundamental innovation was deceptively simple in concept, though hideously complex in execution. Rather than leaving the pilot to extract himself manually, they would use explosives to do it for him. A carefully calibrated explosive charge would accelerate the seat itself upward through the aircraft canopy, carrying the pilot with it. Once clear of the aircraft, a series of mechanical and aerodynamic mechanisms would ensure the pilot separated from the seat and that his parachute deployed safely. The elegance of this solution lay in its brutal directness. Do not help the pilot escape. Remove the problem entirely by extracting both pilot and seat as a single unit, accelerating them away from the aircraft with sufficient velocity to ensure they cleared the tail section. The technical challenges were substantial. The explosive charge had to generate enough force to accelerate a man in a seat weighing roughly 250 kilograms upward through an aircraft canopy at a rate sufficient to clear the tail, yet not so violent that it would kill the occupant through acceleration trauma. Engineers calculated that this required an acceleration of approximately 12 gravities, 12 times normal Earth gravity, applied almost instantaneously. For comparison, a car crash at moderate speed generates around 15 gravities but is experienced over a fraction of a second. The ejection seat would subject a pilot to 12 gravities for approximately 0.2 of a second. The human body can technically survive this. Whether it could do so repeatedly or in varied physical conditions remained entirely unknown. The seat itself had to be engineered as a complete life support system. Beneath the pilot sat a steel framework lined with shock-absorbing material. The seat incorporated restraint systems that would hold the pilot secure during the violent acceleration phase, yet release automatically once the seat cleared the aircraft. Above the seat, a drogue parachute would deploy automatically, stabilizing the seat and decelerating it enough for separation to occur safely. Only then would the pilot's main parachute deploy, allowing him to descend to the ground. Every component had to function independently of the others, because if one failed, the pilot was almost certainly dead. There was no bailout plan. There was no plan B. The manufacturing process required unprecedented precision. Martin Baker tooled up production facilities capable of building the explosive cartridges with exacting tolerances. The pyrotechnic charges had to be identical, batch after batch, because any variation in explosive force would alter the acceleration profile unpredictably. Engineers at the facility in Denham worked with gunsmiths, with chemists, with specialists in materials science, gradually refining the design through thousands of hours of calculation and analysis. Prototype seats were built and tested on rails and test rigs, but these could only simulate the actual forces. They could not replicate the complete environment of a real ejection from a real aircraft. By 1948, Martin Baker was ready for human testing, and here the story becomes not just technically fascinating but genuinely tragic. The company needed volunteers who understood the risks and accepted them anyway. They found these volunteers among the small community of test pilots who worked in the British aerospace industry. These were men accustomed to risk, men who had already survived multiple catastrophic failures, men who believed that progress required sacrifice. The first human ejection tests were conducted from stationary aircraft on the ground, then from aircraft moving slowly along the runway. Each test, if successful, taught the engineers something new. Each failure taught them something else. The breakthrough came with Squadron Leader Terence Spencer on that gray February morning in 1949. Spencer's Gloster Meteor was flown to approximately 350 miles per hour, a speed at which the slipstream would certainly pin any pilot attempting to exit manually. At 10:15 in the morning, Spencer activated the ejection mechanism. What occurred in the next 0.2 of a second would prove that the ejection seat was not merely a theoretical solution, but a practical one. The explosive cartridge detonated. The seat accelerated upward through the canopy. Spencer felt the overwhelming force press him into the seat with the weight of what felt like a small building. The drogue parachute deployed, yanking him backward as the seat decelerated. The seat separated cleanly, and Spencer's main parachute opened. He descended safely to the ground near a farmer's field, where he was discovered calmly making notes about the experience. When Spencer reported his observations to Martin and Baker, they discovered something unexpected. He had not merely survived, he had survived while experiencing something close to consciousness, able to observe details and make decisions. The system worked not just in theory, but in practice. Not just for survival, but for functional survival. More tests followed, conducted from increasingly higher altitudes and faster speeds. By 1952, Martin Baker had demonstrated conclusively that pilots could be safely ejected from aircraft moving at speeds that would have been utterly lethal with traditional bailout procedures. The Royal Air Force began fitting Martin Baker seats to its fighter aircraft. The innovation spread to other nations and other air forces. If you are finding this interesting, a quick subscribe helps more than you know. The algorithm rewards engagement above all else, and your subscription, taking perhaps 5 seconds of your time, makes an extraordinary difference to the reach of this channel. If you've watched this far, you clearly care about these stories, and I'd be genuinely grateful for your support. During the Korean War, which began in 1950 and continued until 1953, British pilots equipped with ejection seats found themselves in direct combat with Chinese and Soviet pilots flying older aircraft. The ejection seats proved their worth immediately and dramatically. A damaged Gloster Meteor could be abandoned at high speed. The pilot would eject and descend safely via parachute, often landing behind friendly lines or in territory controlled by United Nations forces. Compare this to the German experience during the latter part of the Second World War. German pilots, trapped in fast fighters with no effective escape mechanism, faced a binary choice: belly land the aircraft and hope for survival, or stay with it and crash. German ejection seat development had been hesitant and late, yielding only experimental systems that saw minimal use. The Heinkel HE-280 experimental fighter had been fitted with primitive ejection seats, but these remained largely experimental. By contrast, British pilots had a proven, reliable system that had been tested and refined through actual combat use. American pilots, meanwhile, were adopting their own ejection seat designs. The standard American seat, which evolved from various designs during the 1950s, represented a parallel approach to the same problem. American engineers developed systems using similar principles: explosive charges, restraint mechanisms, and parachute deployment systems. However, the American seats tended to be heavier and more complex than their British counterparts. The Martin Baker design was lighter, more elegant in its engineering simplicity, and, according to comparative statistics from the period, marginally more reliable. Over several decades, American manufacturers would eventually license the Martin Baker design, acknowledging the superiority of the British engineering. When the B-47 Stratobomber entered service with the United States Air Force, it was equipped with ejection seats derived directly from Martin Baker concepts. The American Douglas skyrocket test aircraft used Martin Baker seats for its supersonic test program. By the mid-1950s, Martin Baker had become the global standard for ejection seat technology, dominating not just British aviation, but the international market. The actual impact of the ejection seat on pilot survival rates was profound and measurable. In the Second World War, approximately 25% of pilots forced to abandon their aircraft survived the experience. By the 1950s, that figure had climbed to roughly 70%. By the 1960s, with improved parachute technology and more refined ejection seat designs, survival rates exceeded 80% for pilots who actually managed to eject. These statistics do not capture the full impact, however. The ejection seat transformed the psychological landscape of combat flying. Pilots no longer faced the prospect of certain death if their aircraft was damaged. They faced instead a reasonable chance of survival. This knowledge, subtle though it may seem, made pilots more effective in combat. It allowed them to take calculated risks with greater confidence, to concentrate on their mission rather than on their impending death. The ejection seat did not merely save individual lives, it changed the nature of aerial combat itself. Yet this triumph was obscured for decades by secrecy and bureaucracy. The full history of the ejection seat's development remained classified well into the 1970s. The names of early test pilots who suffered injuries or death were rarely mentioned in published accounts. Martin Baker, whilst acknowledged as the manufacturer, did not receive the public recognition its engineers deserved. Terence Spencer himself became something of a phantom figure in aviation history, the man who made the first successful high-speed ejection, yet rarely cited in public accounts of the achievement. This secrecy served various purposes. The military wished to preserve the competitive advantage that reliable ejection seats represented. Martin Baker wished to protect proprietary manufacturing details. And perhaps there was also a desire to minimize discussion of the test pilot injuries and deaths that had preceded success. It is significantly easier to celebrate an innovation once it is proven safe than to discuss the price paid in human suffering during development. The legacy of the ejection seat extended far beyond military aviation. Once the principle was proven, it became a fundamental safety feature for all high-performance aircraft. When supersonic flight became reality in the 1950s and 1960s, ejection seats were there, refined and improved to handle the even more violent stresses of hypersonic bailout. When aircraft began to reach altitudes of 60,000 feet or more, ejection seats evolved further, incorporating oxygen systems and pressure suits to protect pilots in the thin, hostile environment of near-space flight. The Martin Baker seat went through dozens of iterations, Mark I, Mark II, Mark III, and beyond, each incorporating lessons learned from actual use, combat experience, and advances in materials science. Today, almost all modern military fighter jets carry ejection seats directly descended from those early Martin Baker designs. The Eurofighter Typhoon uses ejection seats developed from Martin Baker technology. The American F-16 Viper, despite being developed independently, uses principles that owe everything to British innovation. The Rafale, the Gripen, the Su-27. Virtually every modern fighter aircraft in service carries seats that trace their lineage directly back to the work conducted at Martin Baker's facility in Denham during the 1940s. Surviving examples of early Martin Baker seats can be found in aviation museums throughout Britain and Europe. The RAF Museum at Hendon possesses several examples. The Shuttleworth collection at Old Warden includes original seats installed in period aircraft. But the human cost of their development remains less celebrated, less discussed, and in many cases still incompletely documented. The story of the ejection seat is, at its heart, a story about the price of progress and the willingness to pay it. British engineers solved a problem that others believed to be insurmountable. They did so not through wild inspiration, but through methodical analysis, rigorous testing, and the acceptance of genuine risk. Test pilots, men who understood that they might not survive, submitted themselves voluntarily to increasingly dangerous experiments in the service of advancing knowledge. Some of them were injured. A few did not survive. Their names appear, if they appear at all, in footnotes and appendices in obscure technical histories. yet the innovations they helped prove save lives to this day. Every time a modern pilot ejects from a stricken aircraft and descends safely beneath a parachute, he or she is benefiting from work done by these forgotten pioneers. Every fighter pilot who walks away from an aircraft that should have been his tomb owes his life to decisions made in wartime Britain by engineers who believed the impossible could be engineered. On that gray February morning in 1949, when Terence Spencer felt himself pressed into his seat with the force of a dozen gravities, and felt the violent acceleration that should have torn him apart but instead launched him safely away from his aircraft, something profound shifted in the relationship between pilot and machine. The aircraft was no longer a potential coffin. The machine could still fail, the mission could still go wrong, but now there existed a way out. Now there existed a mechanism, born from human ingenuity and refined through human courage, that made survival possible where none had existed before. The ejection seat was not the product of inspiration or luck. It was the product of methodical problem-solving by brilliant engineers and the courage of test pilots willing to submit themselves to violent forces in pursuit of knowledge. It changed aviation forever. It changed what pilots could do, what they could survive, and what they could accomplish. It did so quietly, with minimal fanfare, in the measured tones of British technical documentation and classified military reports. Yet its impact echoes through every aviation accident where a pilot survives, through every combat where a shot-down pilot ejects and returns to fly again, through every moment in the past 70 years when someone lived who, by all the physics and probability that governed the world before the ejection seat, should have died. That is the true legacy of British engineering at its finest, not celebrated in headlines, but saving lives every single day, year after year, in ways that most of the world will never fully understand or acknowledge.